Imagine standing under the night sky and realizing that just beyond the darkness, in the infinite sea of stars, lies another sun. A small red star called Proxima Centauri, our nearest neighbor in the vast cosmic ocean. It's not hundreds of light years away like most stars you see. It's only 4.24 light years distant. A short hop in galactic terms. Now imagine that this distant point of light hides a secret. A planet, orbiting in the right zone, where liquid water could exist. A world that might even cradle life. And then, imagine the frustration of knowing it's completely unreachable. This is the paradox of our time. We can gaze at Proxima Centauri through our telescopes, we can model its planets on supercomputers, but we cannot touch it. Not with anything humanity has ever built. Imagine a world bathed not in golden sunlight, but in a deep red glow. A sky dimmer than ours, where daylight feels like perpetual twilight. That's what standing on Proxima b might be like. The closest potentially habitable exoplanet ever found. Discovered in 2016 by the European Southern Observatory using the radial velocity method, Proxima b immediately captured humanity's imagination. It's about 1.17 times the mass of Earth, orbiting its parent star once every 11.2 days. Far faster than Earth's 365. At first glance, that sounds scorching hot. But Proxima's small size and faint energy output mean that this close orbit actually places the planet right within the habitable zone. Theoretically, liquid water could exist there. The temperature could hover around 30 to plus 130 degrees, depending on its atmosphere, if it has one at all. But here's the catch. Proxima b is probably tidally locked. That means one side always faces its star, locked in eternal daylight, while the other side remains in endless night. Between these extremes lies a thin twilight band, a region astronomers call the Terminator Zone, where day and night meet in a perpetual dusk. If life exists there, it might thrive in that fragile balance between fire and frost. Now imagine the view. Above you, a sun 3 times larger in the sky than ours, glowing a deep scarlet. Mountains cast long shadows across a copper-colored plain. The night side glitters with frozen clouds of water ice. It's alien, but familiar enough to make you wonder if, just maybe, someone might already be watching us from there. Proxima b is far from perfect. Its parent star flares violently, releasing bursts of radiation that could strip away an atmosphere in time. Yet some simulations show hope. Magnetic fields or dense atmospheres could shield its surface, keeping water intact. And even if Proxima b proves barren, it's not alone. Astronomers have found hints of a second world, Proxima c, orbiting farther out, perhaps an icy super-Earth or mini-Neptune, and maybe even a third, more distant candidate. Together, they might form a tiny solar system orbiting our nearest neighbor, a system we can study, a system we can see. A system that might someday become the first target of humanity's greatest voyage. Because Proxima b isn't just a point of light in our telescopes anymore. It's a symbol of possibility, of the next home we might one day reach. Here's where the dream collides with reality. Because even though Proxima Centauri is our closest stellar neighbor, in the language of space, it's still impossibly far. 4.24 light years. That's about 40 trillion kilometers. To grasp that number, imagine driving at highway speed, 100 kilometers an hour, non-stop, forever. You'd reach Proxima Centauri in roughly 50 million years. Let that sink in. The fastest spacecraft ever built, Voyager 1, launched in 1977, travels at about 17 kilometers per second. That's 60,000 kilometers an hour, fast enough to circle the Earth in 7 minutes. And yet, even at that unimaginable velocity, it would take more than 76,000 years to reach Proxima Centauri. 76,000 years. That's longer than the entire history of human civilization, and Voyager isn't even headed that way. Our most ambitious missions, New Horizons, Parker's solar probe, barely scratch the edge of what's possible with chemical rockets. Every time we leave Earth, we fight against gravity, drag, and fuel. And in that fight, fuel always wins. Because the faster we want to go, the more fuel we need, and the more fuel we add, the heavier the spacecraft becomes, which means we need even more fuel to move it. It's a loop we can't escape. If we tried to reach even 1% of the speed of light using chemical propulsion, we'd need a fuel mass greater than 100 times the mass of Earth. Completely impossible. And even if we could build a rocket that powerful, there's another problem: Einstein. According to the theory of relativity, the faster an object moves, the more its mass effectively increases. The closer you get to the speed of light, the harder it becomes to accelerate further. At light speed, your mass would be infinite, and so would the energy required to move you. No matter how advanced our engines become, physics itself sets the limits. But let's say we don't need light speed. Let's be humble. Maybe 10,000 kilometers per second. At that pace, we could reach Proxima Centauri in about 130 years. Still longer than any human lifespan. Even if we could push that to 25,000 kilometers per second, the journey would still take over 50 years. An entire lifetime, hurtling through the dark, with no guarantee of arrival. So what do? Do we give up the dream? Do we accept that the stars are forever out of reach? No, we rethink everything. If conventional rockets can't carry us to another star, then maybe we need to stop thinking like rocket engineers and start thinking like physicists, dreamers, and inventors. Maybe the answer isn't in bigger engines or more fuel. Maybe it's in new physics, new propulsion, new courage. Because reaching Proxima Centauri isn't just a question of distance. It's a question of imagination. If the old ways can't take us to the stars, then we must invent new ways. Throughout history, every great leap of exploration began when we let go of the familiar, when we dared to build something no one had ever seen before. And so, humanity's quest for interstellar travel has given birth to a new generation of ideas. Some real, some theoretical, all astonishing. Unlike the roaring chemical rockets that blast off from Earth, ion engines don't rely on brute force. They whisper through space, slowly, continuously, efficiently. These engines use electric fields to accelerate charged atoms, or ions, shooting them out of the back of the spacecraft at tremendous speed. The thrust is tiny, about the weight of a piece of paper resting on your hand. But it never stops. Day after day, year after year, the spacecraft accelerates. NASA's Deep Space One and Dawn missions have already proven the technology. They traveled farther with less fuel than any chemical engine could dream of. But even at their best, ion drives would still take tens of thousands of years to reach Proxima Centauri. Beautiful technology, wrong scale of ambition. Next comes the dream of the nuclear rocket. Instead of burning chemical fuel, these engines would use a nuclear reactor to heat hydrogen, blasting it through a nozzle to generate thrust. Back in the 1960s, NASA actually tested this idea under Project Nerva. The engines worked, doubling the efficiency of chemical rockets. But political fear and funding cuts killed the project before it ever left Earth. If revived today, nuclear thermal rockets could cut a Mars trip from 9 months to just 3. For interstellar travel, though, they still fall short, requiring millennia to reach even the nearest stars. But humanity didn't stop there. What if our spacecraft could be powered the same way stars are? Fusion propulsion, combining atomic nuclei to release energy, could unleash power millions of times greater than chemical fuel. Projects like Daedalus, proposed in the 1970s by the British Interplanetary Society, imagined a massive 2-stage fusion spacecraft powered by helium-3 harvested from Jupiter. It could theoretically reach 12% the speed of light, enough to arrive at Proxima Centauri in about 36 years. But there's a problem. We still can't make controlled fusion work on Earth for more than a few seconds. The physics is brutal, the machinery complex, and the cost astronomical. Still, scientists at Icarus Interstellar and NASA's Glenn Research Center continue to chase it. Because if fusion ever becomes practical, it won't just take us to Proxima Centauri, it will change human civilization forever. Then comes an idea so bold it sounds like science fiction. Antimatter propulsion. When matter meets antimatter, the two annihilate completely, turning every atom of their mass into pure energy. 1 gram of antimatter could release the same energy as 40 nuclear bombs. A spacecraft using even a few milligrams could, in theory, reach half the speed of light. But there's a catch. We can barely make a few nanograms of antimatter in a year, and storing it safely is another nightmare. Even a single containment failure could vaporize the ship. Antimatter propulsion may someday be possible, but for now, it remains a dream on the edge of physics. Before fusion reactors, before antimatter, there was a plan both insane and genius. Project Orion. The concept was simple and terrifying. Launch a spacecraft powered by nuclear explosions. Hundreds of bombs detonated behind a giant shock-absorbing plate, each blast pushing the craft forward like a cosmic hammer. Calculations showed Orion could reach 10% the speed of light, enough to make the journey to Proxima in about 40 years. But treaties banning nuclear explosions in space shut it down. Still, the concept lives on in fusion pulse ideas like Project Medusa, where an enormous sail would catch the shockwaves of controlled detonations. Dangerous? Absolutely. Possible? Maybe. Visionary? Without a doubt. And then, there's the frontier where physics turns poetic. Einstein told us that nothing can move faster than light. But what if space itself could? The Alcubierre drive, proposed in 1994, suggests a way to bend space-time itself. Compressing it in front of a spacecraft and expanding it behind, the ship wouldn't move faster than light through space, but it would move space itself. A warp bubble, a pocket of bent reality, and a one-way ticket to the stars. The math works. The energy requirements? Don't. We'd need exotic matter with negative energy density, something that may or may not exist. Still, the idea refuses to die, because every impossible thing we've ever done, flight, electricity, space travel, was once just a dream written in equations. Across all these technologies, one truth remains. We are learning. We are building the foundation for the next leap. The leap from solar to interstellar. And somewhere among these prototypes, theories and dreams may lie the engine that will carry humanity beyond the sun and into the vastness between the stars. If rockets are too heavy and reactors too dangerous, perhaps the answer isn't in the engines, but in the light itself. Because light, even though it has no mass, carries momentum. And momentum means force, a push, tiny, delicate, but relentless. This is the idea behind one of humanity's most poetic inventions, the solar sail. Imagine a spacecraft with no fuel tanks, no exhaust, no fire, just an enormous gleaming sail stretching thousands of square meters, thin as a strand of hair, lighter than a feather. Sunlight strikes its surface, and each photon, each particle of light, pushes ever so slightly. The thrust is small, but constant. Over time, that gentle pressure could send a ship hurtling between worlds. The Japanese probe Ikaros, launched in 2010, was the first to prove it works. A 14-meter sail, spinning through the void, catching sunlight as it traveled toward Venus. In 2019, the Planetary Society's LightSail 2 took the next step, using sunlight alone to raise its orbit around Earth. These were humble beginnings. Tiny ships, slow speeds, but every voyage begins with a whisper. To reach the stars, however, sunlight alone won't be enough. As a ship sails farther from the sun, the light weakens, and the pressure fades to nothing. If we want to go interstellar, we need a new kind of sunlight, an artificial one. Imagine a massive array of lasers, spread across the deserts of Earth, or floating in orbit above it, firing beams of light into the darkness. These beams converge on a reflective sail in space, pushing it with a force millions of times stronger than sunlight. This isn't fantasy, it's physics. When light reflects off a mirror, it transfers twice the momentum. One push from the incoming beam, another from the bounce back. With powerful enough lasers, we could accelerate a sail to a fifth of the speed of light in just a few minutes. That's 60,000 kilometers per second. Enough to reach Proxima Centauri in 20 years. But building such a system is beyond anything we've ever done. The lasers would need to output tens of gigawatts of power and stay perfectly aligned over thousands of kilometers. The sail, likely made from graphene or metamaterials only atoms thick, must endure extreme heat and radiation, without tearing, melting, or losing reflectivity. It would be the most delicate, daring structure ever created. There's another beauty in sail technology. It's scalable. We could start small, tiny chipsats propelled by lasers, each carrying cameras, sensors, and transmitters. Then scale up, kilometer-wide sails for human cargo, or hybrid crafts combining nuclear and photonic propulsion. Some designs even suggest layered sails, with adjustable transparency to steer and stabilize the craft, turning the ship itself into a living, thinking wing of light. Other hybrid proposals, like the Medusa concept, combine sails with controlled explosions, where a massive sail captures the energy of nuclear detonations behind it. It's violent, elegant, terrifying, and maybe one day, real. Sailing the starlight isn't just a new form of propulsion. It's a philosophy. It means traveling without burning, moving without consuming, gliding on the purest energy the universe provides. It's what the ancient mariners of Earth did with wind and waves, and what their descendants may one day do with light and gravity. Because somewhere out there, floating in the eternal black, a thin silver sail could soon unfurl, catching the first beams of humanity's artificial sun, and begin its silent journey toward the nearest star. At some point, every dreamer, every scientist, every engineer stopped asking if we can reach the stars and started asking how soon. That's where Project Starshot begins. Launched in 2016, it's not a sci-fi script or a thought experiment. It's a real global initiative, funded by billionaire Yuri Milner, supported by Stephen Hawking before his passing, and led by former NASA scientist Pete Worden. Their goal? To send a spacecraft to Proxima Centauri within a single human lifetime, and not a massive starship, not a generation arc, but a fleet, thousands of microsatellites, no bigger than a coin. They're called star chips, each one just a few grams in weight, a wafer-thin circuit packed with sensors, cameras, navigation systems, and laser transmitters. They'd be mounted on photonic sails, ultralight mirrors only a few atoms thick, designed to capture laser light instead of sunlight. From the surface of Earth, a colossal laser array, built across kilometers of desert, would focus beams of up to 100 gigawatts directly onto those sails. For a few minutes, the air would shimmer, as thousands of tiny spacecraft accelerated, faster and faster, until they reached nearly 20% the speed of light. That's 60,000 kilometers per second. At that speed, a starship could cover the distance to Proxima Centauri in just 20 years. 20 years to reach another star, something no human civilization has ever achieved, but one we might see in our lifetime. The challenges, though, are staggering. Building a laser that powerful means creating one of the most advanced energy systems in human history. The beams must stay perfectly focused across millions of kilometers, targeting a sail smaller than a car, traveling faster than a bullet. And once the probes reach the interstellar medium, they'll face dust particles traveling at near relativistic speeds. Even a grain of sand could destroy them instantly. So engineers are designing them with protective coatings and angled shapes to deflect collisions. When they finally arrive at the Proxima Centauri system, each probe will pass within a few million kilometers of Proxima b, snapping high-resolution images, measuring atmospheres, magnetic fields, and even searching for traces of biosignatures, oxygen, methane, or vapor that hint at life. Then, each probe will use its own tiny onboard laser to send the data back home. A transmission that will take over 4 years to reach Earth. 4 years of waiting, 4 years of silence, and then the first real photograph of a world orbiting another star. Think about that. The first time humanity sees the surface of an alien planet, not as a blurry pixel on a telescope screen, but as an image, a landscape, a place. If Starshot succeeds, it will change everything. It will prove that we are no longer bound by our solar system, that our technology, our curiosity, and our courage can reach beyond the sun. Even if most probes are destroyed, even if only a few survive the journey, it doesn't matter. Because one of them will make it. One of them will fly by Proxima b and whisper back to us across the void. A signal that says, we did it. We crossed the stars. And that message, when it finally arrives, will mark the moment humanity truly becomes an interstellar species. For thousands of years, we've looked up at the stars and seen stories. We've seen gods, heroes, monsters, myths. But behind all those legends, we've always seen something more. A challenge, a destination. Because somewhere deep inside us, written into our DNA, is a need to explore, to go beyond the horizon, to see what's next. It's what carried our ancestors across oceans and deserts, what built ships, maps, and telescopes. It's what sent the first humans to the moon. And it's what will one day send us to another star. But to make that journey with humans aboard, not probes, not machines, real people, we would need to rethink everything we know about life, death, and time. At our fastest current speed, a human voyage to Proxima Centauri would take thousands of years. That's longer than all of recorded history. So, if we can't make our ships faster, we'd have to make our lives longer. Enter the concept of the generation ship. A spacecraft so large it's a world of its own. A floating city drifting between the stars. Entire generations would live, work, and die inside it, while their children, grandchildren, and great-grandchildren carry the mission forward. By the time it reaches its destination, the people who arrive would be the descendants of those who launched it. Inside these massive vessels, artificial gravity would be created by slow rotation, a spinning cylinder that mimics the pull of a planet. There would be farms, rivers, ecosystems, entire societies evolving in isolation for centuries. Their view of the stars outside would become not a symbol of hope, but the only reality they've ever known. But that kind of journey raises questions as old as philosophy itself. Would those born aboard such a ship feel trapped or chosen? Would they still care about a destination their ancestors dreamed of centuries ago? Or would they simply adapt, making the ship itself their home, and forgetting that it was ever a journey? To solve this, scientists and storytellers have imagined alternatives. Perhaps humans could travel in cryogenic stasis, their bodies frozen for centuries, to awaken at a new star, alive and unchanged. Or perhaps we'll send only our minds, digital copies of our consciousness, uploaded into machines capable of surviving for millennia. Those minds could wake aboard a robotic vessel, build new bodies, new societies, and become the first humans to live beyond the sun. Not in flesh, but in thought. To some, it sounds cold. To others, it's evolution. Because maybe the next step in humanity's story isn't just to travel across space, but to travel across forms of existence. Imagine it. A ship leaves Earth, carrying 1,000 souls, or their digital echoes. Inside, they dream as the ship crosses the interstellar dark, powered by fusion, sails, or beams of light. Outside, the galaxy unfolds, stars drifting past like embers. And when that ship finally arrives at Proxima B, when it slows, or simply flies past, it will be humanity, in one form or another, touching another sun for the first time. That moment, whether it happens in 100 years or 1,000, will be more than a triumph of science. It will be the fulfillment of a story that began before we had words. Because the dream of the stars isn't just about escaping Earth, it's about becoming what we've always been meant to be. A species that refuses to stop reaching. A species that travels not just through space, but through time, imagination, and courage. Why do we want to go? Why spend generations, fortunes, and lives chasing a dream that might never be reached? Because it's who we are. We are the children of explorers, the descendants of wanderers who crossed mountains, oceans, and the unknown. Every step we've ever taken forward was a step into darkness, and every time we brought the light with us. When humanity first built ships, they weren't designed for safety. They were designed for possibility. Sailors didn't know what lay beyond the horizon, but they went anyway. Not because they were sure of what they'd find, but because staying still meant never knowing. The same is true today. We build telescopes, not just to see the stars, but to understand ourselves, to remind us that our little world, as beautiful as it is only one page in a much greater story, and that story is written in starlight. Proxima Centauri isn't just a destination, it's a mirror, showing us both our limits and our potential. It asks us hard questions. Are we content to stay home forever, confined to one planet? one sky? Or will we accept the challenge of the universe and claim our place among the stars? Because space isn't just empty, it's alive with meaning. Every star is a chapter, every planet a possibility. To explore them is not vanity, it's survival. Someday Earth will change, our sun will age, the oceans will shift, and continents will break apart. Long before that, humanity must learn to move, to adapt, to expand, to live beyond the cradle. Exploration is not a luxury, it's a necessity. It keeps us learning, unites nations, and reminds us that we belong to the same fragile world. Every mission launched, every rover sent, every signal received is a small victory over extinction, because to explore is to endure. To explore is to say, we will not vanish quietly into the dark. And when we look back on history, we'll see that our greatest achievements weren't wars or empires. They were moments when we reached beyond what we thought possible. Moments like the first step on the moon, the first image of a black hole, the first signal sent across the stars. Each one whispered the same message. We can go further. And someday soon, that whisper will become a voice. A signal from a tiny sail of light, racing through the void saying, we made it. Humanity has arrived. At the end of all the science, all the equations, all the engineering, what remains is something far older. A feeling. The same feeling that made our ancestors look up at the night sky and wonder what those lights were. The same feeling that made a young species, born in caves and forests, dare to reach for the heavens. That feeling is still here, and it's what will carry us to the stars. Reaching Proxima Centauri isn't just about technology. It's about courage, patience, hope. It's about believing that humanity, for all its flaws, for all its struggles, is capable of greatness. Every breakthrough we make, every discovery we share, is another small spark of light pushing back against the darkness. And together, those sparks form a constellation. A map showing the path forward. Because one day, not far from now, a new kind of sunrise will appear. Not over mountains or oceans, but over an alien horizon beneath the crimson light of another sun. A human voice, or maybe the hum of a machine carrying our thoughts, will speak into that strange air and say, we came from a world called Earth, and now we are here. That moment will not belong to one country or one generation. It will belong to everyone who ever dared to look up and imagine. It will belong to every child who traced constellations with their finger. Every scientist who stayed awake through endless nights of equations. Every artist who painted worlds that didn't yet exist. Because the stars have never belonged to anyone. They've always belonged to those brave enough to reach for them. As Carl Sagan once said, when we are ready to visit other stars, we will no longer be the same. He was right. When that day comes, we won't just be travelers or scientists. We'll be storytellers of the universe. A species that turned imagination into destiny. The universe is vast, silent, patient, waiting. And somewhere out there, under the light of Proxima Centauri, a reflection of Earth may be waiting too. Our journey has not ended. It has only just begun, because the stars are calling. And this time, we are ready to answer.